next topic is derivation of Hamilton's principle, which can be given as line integral t1 to t2 delta L into dt equals to 0. So we can derive it as, we know that Fi equals to mi ria, which is nothing more than Newton's second law of motion. It can be written as Fi minus mi ri double dot equals to 0, and taking dot product with del ri, which is virtual displacement, we have Fi minus mi ri double dot and dot ri equals to 0. Summing over whole system, we have summation I equals to 1 up to n, which means that a system of particles consists of n number of particles on which force Fi is acting and mi double dot acceleration is producing. We have this equation as Fi minus mi double dot into dot ri equals to 0. Separating, we have I and Fi dot del ri minus mi summation I ri double dot ri equals to 0. F dot del ri means here we have virtual work as Fw equals to Fs, and this minus mi partial I ri double dot partial ri equals to 0. Say equation 1. Now let d over dt equals to ri dot del ri equals to first function as it is derivative of second d over dt del ri plus del ri, and derivative of first term, which means double dot. It can be written as ri dot, taking or changing it the operators, we have del into d over dt ri plus partial del ri into ri double dot, and it can be written as ri and del ri dot plus ri dot ri double dot and d over dt ri dot ri. Equation 3. Multiplying by mi and taking summation on both sides, we have mi taking summation d over dt ri dot del ri equals to mi summation I and ri del ri plus mi summation del ri dot ri double dot. Here we will see this equation is same as this equation, so this term can be written as here mi summation I del ri dot ri double dot equals to mi summation I d over dt dot ri minus this term will be this side will be minus mi summation I ri dot. Say equation 4. Now here we will see that this term. Now let again part del ri dot ri can be written as ri dot del ri plus del ri into ri as a dot b and b dot a, so we can write it as equals to ri dot del ri into 2, or 1 over 2 del Ri dot Ri equals to Ri dot del Ri. Multiplying by Mi and taking summation, we have Mi taking summation Ri dot del Ri equals to Mi summation 1 over 2 del Ri dot Ri. Say, and it can be written 1 over 2 m Ri dot Ri means v square, and it can be given as del t, equation 5. Put equation 5 in equation 4, we have Mi summation I del Ri dot Ri double dot equals to Mi summation I d over dt Ri dot del Ri minus del t, which is equation 6. Now put equation 6 in equation 1, we have del w minus mi summation I d over dt ri dot del r I minus minus plus del t equals to 0, or del w plus del t equals to mi summation I d over dt ri dot del ri. Taking derivative on both sides and then integrating t1 to t2, we have w plus t into dt equals to mi summation d over dt ri dot del ri into dt time t1 to t2. We will have mi summation I into ri dot del ri limit t1 to t2 equals to 0, and here we have t1 to t2 del w plus del t into dt, say equation 7. Here summation mi ri dot del ri t1 to t2 equals to 0, but how? As we know that del Ri is a function of del Qj, and del Qj are fixed at endpoints, and as they are fixed means they are stationary with respect to time, or del Qj at t2 equals to 0, del Qj at t1 equals to 0, or we can say that del Ri at time t1 to time t equals to 0. That is why we take it 0, and we have t1 to t2 del w plus del t into dt equals to 0. Say equation 8. Now we know that fi can be given as del minus del I into v, or fi equals to minus partial v over partial ri. We can written it as fi dot partial ri equals to minus partial v, or fi dot del ri equals to minus del v, and it can be written as virtual work, which is minus del v. Say equation 9. Put equation 9 in equation 8, we have t1 to t2 and del t minus del v into dt equals to 0, or t minus v dt equals to 0, and t minus v is a Lagrangian function. So here is the proof of what we want to find, which is Hamilton's principle.